Hey, it's fall break, and I don't want to occupy you guys a lot of time, so I will quickly go through like the two homeworks of this week. First one is mostly some graphing techniques, and the second homework assignment involves some t-test and the z-score test. So I just set up my mini tab. Can anyone see my shared screen?
Yep.
All right, thank you. I'll post the recording anyhow. So basically, for the first homework, like we're gonna generate a random, I think 10,000 data that is coming from an exponential distribution, and then we're gonna add them up to form a new distribution. The way to do it is you go to calculus and random data, I think. Yeah, random data. And here you have exponential. So go to calc, random data, exponential. You want to generate 10,000 data. I store in first column C1, the scale, which is the parameter in the homework is 1.0. That means the 10,000 random data I'm generating have a mean of 1, and they are exponentially distributed. I click on OK, and here I have 10,000 data. The new student coming in, I just use calc, random data, exponential, and I set the parameter equals 10,000, which is the number of data I want to generate. I store in column C1. I put the scale, which is the mean, and that's the parameter in the homework. I set that into 1.0, and that's my C1. So then I'm gonna plot them. I'm gonna do histogram because I have 10,000 data set. Like I cannot just scroll down the screen and to see like what are some personalities of those 10,000 data set, right? It's impossible. It's too many. So the most simple one is I do a histogram and to see what's the pattern of those 10,000 observations. And here it is. Looks pretty exponential. Make it even bigger. That's the 10,000 data set I'm generating. You see there is more than 16,000. Data has a value like between I think 0.2 0.4 something. There's a lot of data around 0, and just be aware that those 10,000 data I'm generating have a mean of 1.0 something here, right? So you can see like my mouse is showing a vertical line that the area of the right and left of this vertical line of x equals 1 of like they basically have the same area, the right and the left. So those are the histogram of the 10,000 data set I'm generating. Then I'm gonna plot a QQ plot. I think it's the probability plot. Yeah, here it is. Like maybe you're gonna input some other command, I think, because I already did that, so it gives me a QQ plot against a standard normal distribution. But if you do it like the first time, maybe you should input some other command, like I'm plotting my C1, my data against a standard normal distribution. So here the red line, basically the red line is what it looks like of a standard normal distribution with mean 0, right? So just first focus on the red line. The mean is 0. And here I have a negative 2.5 in the x-axis. That is 2.5 standard deviation lower than the mean. And if you look at the intersection, like the intersection between x equals negative 2.5 and the red line, and you see the y value is just a little bit greater than 0.01%, right? 0.01% is just like 0.0001. So you get like from a standard normal distribution, it's very unlikely to observe like a data point which is 2.5 standard deviation away from the mean, right? And that gives you like a basic intuition of how that red line works. And if my data, my column of C1, if they have exactly a standard normal distribution, then my blue dots, which are my observation, the blue dots will perfectly align with the red line, like forming a straight line. But here, obviously, it doesn't, because my C1 column actually it is 10,000 observations of an exponential distribution, not a standard normal distribution. So we can see it has a very fat tail on the right, like here, very fat tail on the right, and a very small tail on the left, right? And we can see it from the histogram actually. If we look at the histogram, it does have a fat tail on the right, like a standard normal distribution, like a bell curve. It doesn't have that much tails on the right, and it has a little bit more tails like on the left. So that's the very basic like differentiation between a normal distribution and an exponential distribution. And like we can view it through this QQ plot. For some other questions, you just need to generate like 10,000 data set, like 2 times, 5 times, and 10 times, and sum them up. The way I am doing it is like I just sum it, I just generate it like in a column, and then I copy paste them to another column, and so on and so on. So it takes a lot of time, but I don't know if there's some shortcut like you can generate it 10 times like in the single column without replacing the original ones. I don't think it's doable in Minitab. So what I did is I just generate 10 times, and each time I copy 10,000 data and I add that 10,000 data to the next column. Kind of wasting of time, but I think the baseline of this question is you will get a sense of if you add 2, 5, 10, right? If you add 10 identically independent exponential distribution, and you form a new distribution, what does it look like, right? What does the new distribution looks like? You can plot a histogram, you can plot your data in a QQ plot, and you see like, okay, what new distribution I'm forming. For the last question, it's basically the same procedure. Something I want to point out is in financial data, right? They're systematically they have a fat tails. Some people call it leptokurtosis, meaning it's not like it looks normal, like the stock returns. Sometimes it's positive, sometimes it's negative. The mean very close to zero, and the stock returns. Right, today I earned 2%. Next day I lose like 1%, 1.5%. Like it looks pretty normal, perfectly and symmetric around the mean, which is zero. However, those financial data always have like a fatter tail than normal distribution. So for the last question, you're gonna plot the stock returns, and if you plot all your data in the QQ plot, you won't find a perfect straight line. You won't find a line like this red line because you have a fatter tail, which means you're more likely to get some abnormal observation, which lies maybe 4 or even 5 standard deviation around the mean. In a perfectly standard normal distribution, it's nearly impossible to find a data lies 4 or 5 standard deviation beyond the mean. However, it happens in financial data. So that's also a hint that when you're doing finance, right, you're gonna always think about your risk because it's very likely to get an abnormal data, and it just happens. Next, I'll talk briefly about the next homework. Okay, for the first problem is a pretty standardized t-test. You use the mean of your observation minus minus your null hypothesis. In this case, your null hypothesis is mu equals 0.338. So it's x minus mu divided by the standard error of x. It's a very standardized t-test. So and for part B, there's two ways to address it. Like first, you're gonna do the t-test again. However, you just use mu equals 0.28. For part B, we'll use mu equals 0.338 in part A. Right? You can do it again. Another alternative for this question is you can use the result of part A, and you can do a confidence interval, like a 95% confidence interval, and to see if 0.28 is included in that interval. So basically you have two ways to address it. But it's a very standardized t-test anyhow. For question 2, it becomes a little bit tricky because here you're not going to use a t-test. Here you're going to use a z-score test. The reason is my scaling evaluation forms like a binomial distribution because I have two results, right? Increasing or not increasing. It's a hint of binomial distribution because just remember one characteristic of binomial distribution is you always have two results. You toss a coin, it should be either heads or tails. Here, it should be either like increased or not increased. So basically I have a binomial distribution. And then I took some sample. I think I took 33 samples maybe. So basically my binomial distribution could approximate a normal distribution because of the central limit theorem. I have enough observations here. And my argument here is, right, I did an experiment and I took out a sample which consists of 33 observations, and then I find the mean of my observation, which is I guess 0.73 something, which is higher, way higher than 60%, way higher than 0.6. However, I'm not sure if the real population mean is 60% or below, right? I find some sample, random sample, I measured their mean, which is like around 70%, which is good. However, because I only take out 33%, like I only take out 33 observations, it's not a very huge sample. So I'm not very confident if the real population mean is greater than 60%. That's the argument. We're gonna do a z-test, and you have your mean, then you're gonna have the standard deviation of your mean, which for binomial distribution it's MPQ. It's a variance, and the square root of MPQ is the standard deviation. But here, there's two ways to address like the variance and standard deviation. The first one, like I said, MPQ, it's for the level, it's not for probability. Like if I have 33 people and I find their probability, I know like among 33 people, like how many of them have like an increased scan evaluation, how many of them have not increased scan evaluation. And so those numbers are just positive integer, right? That's something I call it level. For those kind of data, I use the square root of MPQ. Where here you can definitely use it. But another way to do this is you just want to find the standard deviation of the probability. Like I said, the probability of an increased scan evaluation is around 70%. Then the standard error of that probability is no longer square root of MPQ. It's instead the square root of I think it's PQ divided by N. And by the way, you can try like those two methods and you get exactly the same result. One is the standard deviation variance for the level. One is the standard deviation and the variance for the probability. Should give you the same result. And you're going to use a z-score test where you have your something like x minus mu divided by the standard deviation. You know how to calculate standard deviation, you know how to calculate the mu, and your observed data, which is your observed probability around 70%. So basically you have everything you need to do a z-score test. The mu is just 60% in this case, because I'm assuming the population mean is just 60%. So that's my mu. And then I get my z-score. If that z-score is abnormally large, which means there's very small possibility, there's lower than 5% possibility that the population mean is actually 60%. So I reject the null hypothesis, saying, all right, the population mean is actually higher than 60%. I think something should notice in this question is you do a z-score test, you do a 5% p-value, right? But what is the critical z-score? A lot of times when you think about like 95% interval, you think about a z-score of 1.96, I think. Here is not the case. You're not gonna compare your z with 1.96. The question of that 1.96, that number, is it's a 95% z-score of a two-tailed test, like 2.5% on the left, 2.5% on the right. And if you find the cutoff of that z-score, you can do it in the z-score table. You can find it. It's 1.96. Here, however, we don't want that 2.5 on the left, 2.5 on the right, because I'm doing a one-tailed test. Because my observed probability is around 70%. So I already have some evidence that maybe the population mean is something greater than 60%. My population mean should be around 70% or so. So I'm trying to reject, or like I'm trying to prove that our population mean is more than 60%. I'm not trying to argue my population mean is not 60%. But if I'm doing it, like my argument is my population mean is not 60%, then it could either be less than 60%. It could be also, maybe it could be more than 60%. So I'm gonna do a two-tailed test. But here I'm only doing a one-tailed test. So my 5% p-value is real 5%. In a two-tailed test, a 5% a 5% p-value is actually 2.5% on the right and 2.5% on the left. So there's a difference. I guess the z-score you're gonna compare is like 1.65 something, which is the one-tailed 95% z-score. All right, here for the last question, you need to get the data set from your slide. I guess Darwin's data is like one of the examples you did during the lecture. And the basic idea here is you take the difference of two groups. My null hypothesis is the two groups are same, like although they use like different ways of fertilizing, I think. Like I don't exactly recall that example, but basically you're using two cultivation method for the two groups. And then your null hypothesis is, okay, those two groups, they actually identical. There's not a productivity increase, right? There's no productivity increase. And the way we want to form that null hypothesis into like a statistical context is we find the difference, right? If it's really identical, like those two groups, they are not different at all, then around half of the time I get a positive difference. Around half of the time I get a negative difference, because those two are just similar, they're equal with some errors, with some error terms, some volatility. However, if the two population they actually equal, then I minus the group A from group B, then half of the time I get a positive sign, half of the time I get negative sign. However, using that, so basically here I think I have 15. I have 15 data on each groups or so. So basically, if my null hypothesis is true, then I find around 7 or 8 positive signs and also 7 or 8 negative signs. However, in that data set, I think I can find uh, 13, something like 13. I don't recall like the precise number. Maybe I get like 13 positive numbers, and that is an evidence that maybe one group is systematically better than another group, because 13 out of 15 times group A has a higher number than group B, right? That's how we take the difference and get a positive number. So the probability of that is just what is the probability of getting 13 positive signs out of 15 positive signs? Oh, sorry, what is the probability of getting 13 positive signs out of 15 observations? Under our null hypothesis that the probability of getting a positive signs and the negative signs is equal, is 1.5. So we can just reframe this question into what's the probability of tossing 15 coins and get more than 13 heads. That's our p-value, and you could see that like that p-value should be very small, should be less than 5%. So that's the evidence to reject the null hypothesis and see there's first group or second group, whatever, it's systematically higher, and in this context it's systematically better than the second group. So I think that's everything I want to address. If you have any other questions, please just raise your hand or just unmute yourself.
Did you say the data is in the slideshow?
Yes, I think it is the Darwin's data.
Oh, okay, thanks.
Yeah, you can go to the I think the announcement where Professor Bartman uploaded some slides, I think, in PDF files or like I don't know, in PowerPoint, I think.
All right. Thank you, Victor. Have a good night.
You too.
Have a good night.
You too. Good night.